Hi there, welcome back to Weather Analysis with Mr. CB. This is numerical weather prediction continued. So sorry that my voice is kind of messed up right now. I'm coming off of a cold here, so I'm not feeling the best, but we'll get through this. So we want to talk about model limitations. So we have a lack of observational data both vertically and horizontally at times. It's important that if we have a model that's high resolution, it does not mean that we have increased accuracy always. Um, Interpolation exists where the surface observations are missing, so that can result in errors or limitation. If we have inaccurate analysis, we can have inaccurate forecasts. We already talked about this in the last video a little bit, but we also have boundary errors that exist. And this is just basically inconsistencies that exist on the boundary of our domain. We can have the loss of mesoscale features. For example, a short wave may be missed due to its size relative to the model's resolution, but that short wave may still be very relevant for the conditions that we're going to have. This also applies to surface topography because subtleties in the topography may be missed. We also have parameterization. We talked about that in the last video. Um, and we have parameterization of physical processes. So physical processes must be accounted for, but they are oftentimes have to be parameterized. Convection has to be parameterized in certain cases. Now let's talk about the GFS model. The GFS model stands for Global Forecasting System, and it is produced by NCEP. It is a part of the global domain. It has 127 vertical layers. It has 13-kilometer horizontal domain. It's ran at 0Z, 6Z, 12Z, and 18Z, and it runs out to 384 hours in 3-hour increments. It's important to talk about some common biases that exist with the GFS model. So the strength and speeds of systems crossing the Sierra Nevada mountain range after 36 hours is typically too aggressive for the GFS model. Um, there's often a too aggressive flow with the pattern during the meridional flow. The phasing of the subtropical jet and polar jet during the cool season, and then it's prone to errors with lee side weather systems and cold air damming. Now let's talk about the NAM model. This stands for North American Mesoscale Forecast System. It's produced by NCEP once again. It has 60 sigma pressure hybrid levels, and this one has 12-kilometer domain. There is also the NAM 3-kilometer, and let's look at the difference between the two. The NAM forecasts up to 84 hours in 3-hour increments. It's ran at 0Z, 6Z, 12Z, 18Z. The NAM 3-kilometer has four nested 3-kilometer domains and one movable high resolution nested 1.5-kilometer domain. They forecast up to 60 hours in 1-hour increments, and it's ran at 0Z, 6Z, 12Z, and 18Z. Let's talk about the RAP and HER. The rapid refresh model is what the RAP stands for, and the high resolution rapid refresh is what the HER is. They're both produced by NCEP once again, and they're initialized by the GFS. There are 50 sigma layers and two versions are RAP and the HER. The RAP has 13-kilometer horizontal domain. It can forecast up to 21 hours in 1 hour increments. The HER is higher resolution with 3-kilometer horizontal domain, forecast up to 48 hours at 0Z, 6Z, 12Z, and 18Z, and 18 hours for all other times. Now let's talk about the Euro model, which is ECMWF. This stands for European Center for Medium Range Weather Forecasts. This model is typically considered the most reliable. Its global domain spectral model, 137 hybrid pressure or sigma pressure hybrid levels, um, 16-kilometer horizontal resolution, runs at same times 0Z, 6Z, 12Z, 18Z, runs out to 144 hours in 3 hour increments. The last thing that we're going to talk about, things to consider. How are the models handling the current conditions? What are the model trends? And how does the model output compare to climatology? These are some things that we're going to want to use to determine if a model is a good choice for a certain situation.